So assignment 3, found on page 96 of the current edition of the student workbook, is somewhat similar to assignment 2, where you plotted all the suns, except there was 12 suns to plot. How many moons do you have to plot here? Yeah, 32, so it's a bit more time consuming, except your old hat at it now, you're pretty good, so it goes pretty fast still. But its intent is to help us to answer all the questions about the monthly motion of the moon, which we normally call annual motion, but in the moon's case, it's so fast that it's actually once per month. So it's called monthly motion. And that's part B on page 102. So before you get to part B on 102, you really want to do assignment 3. So let's go over how you do this. All the data is on page 96. You'll see the sky charts on the following 2 pages, both 98 and 100. So do I have that right? It's 97 and 98, 99. So we got day 0 to begin with, and then day 32 to end with. It looks like day number 1 is missing, and it is. So there's a 2-day jump between the first data point and the second. But then every data point thereafter is at 1-day intervals. That'll make more sense in a little bit. But looking at day 0, the right ascension of the moon is 14 hours and 19 minutes and a declination of negative 12 degrees. So, okay, right ascension is 14 hours between 12 and 24. That's definitely summer sky. So flip on over to page 99. And I will too. 14, 19, and negative 12. And okay, so I got my Ceti Scorpius down there. All right, so 12 hours is the far right. 13 hours of right ascension is the first of the major hour marks going left. 14 is here, and I needed 14, 19. Good. So 14 hours and 15 minutes is right where the black and white hash marks interface. And I need 1419, which is about 5 minutes more right about here. I'll make a dot right there at 14 hours and 19 minutes on the celestial equator. And then draw a vertical line through that point, like I just did. So get a straight edge and go right through that 1419. What do we call the vertical lines on sky charts again that intersect the celestial equator at right angles? Yep, those are all hour circles. So everybody on that line has the same right ascension of 14 hours and 19 minutes. All right, and the declination was negative 12. So find the closest vertical axis, probably on the right over here. And the declination values are the numbers going up and down. So 0 degrees declination is the celestial equator. Negative 10 is located here, and negative 20 is there. I need negative 12, which is 2 tick marks below. Make a mark right there at negative 12. It'd be okay to do on the central axis as well. Negative 12 is right about here. And then grab your straight edge and go horizontally right through that mark, just like I just did. What do you call these horizontal lines on a sky chart? Yep, they're called parallels of declination. So where the 2 intersect is the moon's true position that I'm looking for on day 0. So give me a Spica-sized or an Antares-sized dot at the intersection. Here's Antares, there's Spica, about that size dot. And it's not a specific date, it's just day 0 for a random month. So just put 0 next to it. Yeah, the first of the data points. Then you look back on page 96 and you find out that day 2, remember, there's no day 1, but day 2 is at 1610 and negative 21. So, okay. Take the right ascension, 1610. Go along the celestial equator with me. 15, 16, there's 1615, where the black and white interface is, and 1610 is about right here. Make a mark. And give me the vertical line right through that point. I get a little wiser this time. I looked ahead of time and saw the declination was negative, so I really only care about the half that's below the celestial equator. And the declination was already negative 21, so I think I'll use the central axis. There's negative 20, there's negative 30. M8 and M20 are at about negative 24, and I need negative 21, which is right there. I make a mark, put my horizontal and straight edge through that point, and just enough to intersect the hour circle that I just drew. So shorter lines, I don't need them all across the entire page if I kind of keep my wits about me. And at the intersection of those 2 lines, hour circle and parallel of declination, give me an Antares-sized dot. It's awfully close to Antares. And put day 2 next to that point. Remember, there's no day 1. So that jump between these 2 points represents 2 days, and all the other data points are 1 day apart, so you'll expect them to be even closer than you see here. Day 3 is at 1705 and negative 24. 17 is right here. 1705 is about there. Negative 24 is about where M8 and M20 are, so right about where my cursor is located. I'm expecting to get my moon eventually. And I crisscross it, hour circle and parallel declination. Guess I was off by right a cent a little bit. Yeah, 1705, that looks better. And right where those two intersect, give me the anterior-sized dot again and put day 3 next to it. You know, you repeat what? Only 29 more times. Day 4 is about here. There's day 5, day 6, 7, 8, 9, 10. And if I pause just for a little bit, what does that construction remind you of? Looks like those points are all making a kind of a nice smiley face curve, right? And it kind of reminds you of the sun's path, doesn't it? Especially on the summer sky chart. So if you're already guessing that the moon's path is going to look very similar to the sun's path, the answer is you're pretty much right. They will not be perfectly the same, but they are close to each other. Okay. You're going to run out of real estate here in another data point or two. You'll get day 11 and day 12, almost right on the celestial equator itself. Then you got to go to the other sky chart for day 13. So, you know, expect that. But you will come back to this page. And you'll eventually get back to the right-hand side of this page when you get to day 25. There's day 26, 27, 28. And I pause at day 28 on purpose because day 28 will get you past day 0 where you all started. So you're eventually going to be asked, you know, how long does it take the moon to go around the whole sky once? And the best response to that is with respect to what? And I say with respect to the background stars. So how long will it take the moon to get in front of the same background star again? Yeah, get back to the 0. And that's in between day 27 and day 28 because you began on day 0. That's why. So if you said it's about 27 and a half days to do that, I'd say perfect. That's about right. Spot on. We'll be a bit more exact to call it about 27 and a third days eventually, but it's about 27 and, you know, a fraction thereof to get back to the same star. Now, what does your intuition tell you? Do you think it'll look like the same moon? Do you think it'll be the same phase after 27 and a third days? I think if you're a rational person, you probably say, yeah, I would expect it to be. But we're going to find out that it's not. So, that's bizarre. We'll have to figure that out too. But the moon gets back to the same constellation basically in about 27 and a third days. And that's not what you and I call a month. We don't have 27-day months, do we? So, yeah, the period of phases, the time to go from full moon to full moon is longer. And that's more characteristically what you and I call a month. Now, notice there's more data points. So there is a day 29 and a day 30 and a day 31 and a day 32. And if I put them all on there, I mean, what a mess. You know, you see all these crisscrossing lines. But the whole purpose for having day 29, 30, and 31 and 32 is so that you realize they don't perfectly overlap the original. And there's a small askew to the two paths, even just a month apart. Yeah, the moon's orbit precesses, it changes, it wobbles, and therefore from month to month it is not perfectly the same. That's confusing. But does it quickly get back to, you know, a sort of a small zone of error? Yeah. But still, you know, it kind of proves the fact that from month to month it is ever so slightly different. Now, through the magic of PowerPoint, look what I get to do. I hit a button and all those lines disappear. Isn't that much nicer? Then I see all my data points and I go, oh yeah, sure enough, looks an awful lot like the sun's path. Sure does. Yeah, what's the dead giveaway that it's not the sun's path? I know on the far right side of a summer sky chart that you got the autumnal equinox. Yeah, 12 hours of right ascension over here. And if I drew a line between these blue dots for the moon, it wouldn't go perfectly through the autumnal equinox. If I did the same thing over here on the left and drew a nice line through, you know, 10, 11, and 12 for the moon, it wouldn't go perfectly through the vernal equinox either at the 0 right here. So there's your first clue that it's not perfectly the same as the sun's path. Now over on the winter page, days 13 through day 24, here's the winter page. Day 13 or 12, you can overlap them. It will be on the far right, and then, starts to climb, kind of like the sun did on the winter sky as well. And then comes back down again to, day 24 over here. And again, you can tell that the path is not going to go perfectly through the two equinoxes. It won't go perfectly through the vernal, and it won't go perfectly through the autumnal either. And when the moon reaches its most positive or greatest declination, it's going to be a little bit higher than the sun does as well. How high was the sun's maximum declination? Yeah, 23.5 degrees. And the moon's going to get up to being above 25, clearly. Yeah, there's the 25 mark right here. So again, they're not perfectly the same path, but they are similar. If I take away all the crisscrossing lines, and I draw you a nice smooth path through all those blue dots, now you see it, don't you? The slightly askewness to the path of our moon. It's not identical to the sun's. If I put the winter and the summer sky charts side by side, the overall path looks like this. And again, at just first glance, it sure looks like the sun's path, but here's the sun's path superimposed on top. There's the ecliptic, the sun's path. And the blue path is the moon's. And they're off by as much as, well, you tell me, what's the biggest gap you see over here? Or the biggest gap you see about here? Or the biggest gap you see about there? In terms of declination, it's about a 5-degree gap between these two paths. But now you know why eclipses are kind of rare. If these two paths were the same, then every single month, when the moon zipped around, it would go in front of the sun and thereby eclipse the sun. But now we see there's really only two opportunities throughout the course of the year where the moon can get in front of the sun and block it out. And likewise, when the moon is opposite, then of course the moon can get into the Earth's shadow and cause a lunar eclipse. But they are rare because of the fact that these two paths are not identical. We'll call the crossing points between the two paths nodes. There's a node right here, and there's a node right there. And it's the only time that eclipses are possible is when they both show up at that same point at about the same time. And some years they don't, they show up there, or some months they don't. They show up, the moon will show up and the sun's on the other half of the sky. So it's just not the right timing. By the way, we call the sun's path the ecliptic, the path upon which eclipses can occur is its translation. We think they call the moon's path, well, if you call the sun's path the ecliptic, what should they have called Luna or the moon's path? Yeah, the lunatic, right? But no, they already used that word for something else, so we don't call it the lunatic. But when you call somebody a lunatic, you're calling them crazy literally from the moon. So who are the famous mythical creatures you know of that are lunatics? Yeah, werewolves. Yeah, werewolf are the ultimate lunatics, crazy from the moon. All right, get assignment 3 done before you begin part B, the monthly motion of our moon, on page 102.